Hello friends, last class I have started with the light source materials there are the two kinds of the light source materials. One is the light emitting diode and another is the laser diode. Okay, in the next lecture I will start with the laser diode. Today I will discuss some point of the light emitting diode and some numerical associated with the light emitting diode. So, two different types of the light emitting diode we have already discussed. On the surface light emitting diode and another is the edge light emitting diode. The short form of this surface light emitting diode and the edge light emitting diode is short form, you can call it as a SLAD and the EL-LED. Okay, so if you remember the structure of the surface light emitting diode will be like that. There will be the layer structure. So on top of the surface, you can couple the fiber, and the edge emitting diode, you can see that edge of the fiber we can couple the edge of the device we can couple the fiber. Okay, so that's why the surface emitting diode, the light emitting diode, that can give the more power as compared to the edge emitting diode. Okay, so here in this diagram that you can see the forward current versus the light emitting diode. So here you can see the surface light emitting diode can provide the more amount of the power as compared to the each light emitting diode. Okay, and apart from that, what I will told, it can radiate the more amount of power. So that means if you want to more forward current is required for high optical power. Okay, so you need the forward current for optical power. So if you see the spectrum with the spectrum with that is normally large as for case of the surface diameter as over the H light emitting diode. So here in this case you can see this is the surface light emitting diode. Surface light emitting diode is the spectrum region is narrow as compared to the H light emitting diode. So if you also increase the temperature, so the H light emitting diode that can totally the highly dependent on the temperature as compared to the surface light emitting diode. So the highly dependent means the efficiency. Normally, if you increase the temperature, efficiency of the LED can decrease. So it can decrease the output. So in case of the edge emitting diode, edge light emitting diode, normally this is totally highly dependent on the temperature. That means if we increase the temperature, so there will be degradation of the efficiency of the edge light emitting diode. So that the efficiency will not get the high amount of the power from the edge light emitting diode. These are the some different characteristics between the surface light emitting diode and the edge light emitting diode. So now come to the one more point, that is the most important point of the modulation of the LED. Modulation means that means when LED that is also acting as one kind of the system. So you are giving on electrical signal, you are getting one optical signal. Okay, here you are giving the electrical signal, you are getting the optical signal. So the rate at which you are giving the electrical signal, suppose this is the electrical pulse. The same pulse you should get at the output side for case of the system. Okay, same pulse you should get. So but you should not get the same pulse at the optical pulse at the output side, because there will be a some process. It takes some time to generate from the electrical signal to optical signal, due based on the types of the material, based on the physical phenomena, the how the working principle is happening. So based on the everything depend the rate, time rate, the rate required to switch between the electrical to optical, that rate will also decrease. Okay, so the response time, you can see there is one term, the response time on the frequency response of the optical, how fast the electrical input signal can drive the optical signal. Okay, can drive the signal, can vary the light of photon. So how fast the electrical signal can provide the optical signal, that depends the response time. Okay, so that's what I told that the response time that depends. If the response time more, then you will not get the exact shape of the pulse, whatever shape of the pulse you are getting for the electrical signal. The response time is fast, and you can get the high same pulse as compared. Suppose in the this is the input signal. Okay, if the response time is low, then you can get the same pulse at the output side. But if response time is high, so you are not will get such kind of the pulse you will get at the output side. So why this thing is happened? Due to some various reason. One is the doping level, injection carrier lifetime, parasitic capacity. These are the factors which influence the response time of the light emitting diode. So the output optical power that can be defined as a P omega is equal to P omega naught into 1 plus omega tau I square root under. The minus of means root under. That means the P naught by root under 1 plus omega tau I by whole square. Okay. So the P naught means the if we're not giving any signal. So if we're not giving any pulse signal. Okay. Suppose you are giving some DC signal, you are getting the, so there will be no concept of the this thing. Okay, so one constant output you are giving or getting the constant output. So but if you're giving the signal depends on the frequency, that depends on the frequency, the pulse you are giving, right, which depends on the frequency. That means the this the P omega means the output power. Okay, output power, this is the initial power which depends on the frequency. Suppose this is electrical signal. Okay, so either you should get this one in the ideal case, but you should get this one. So that depends on the frequency, how fast the electrical signal or you are getting can respond to get the optical signal. Okay, so this depends on the frequency. This modified signal, the modulated output, this depends on the frequency. That's why the equation is like that, depends on the frequency. The output power that depends on the frequency. If you are getting the omega is high, the high frequency signal you'll get means, so this is called the high frequency say pulse. This is called the low frequency pulse. Okay, so if you will get the omega is high, okay, that means the output is identical to the input. If omega is less than the, you can tell that the output is not identical to the input. So that bandwidth you need to, which frequency the optical signal, up to which frequency the optical electrical signal provide the optical signal. Okay, that means if frequency is low, that means you are not getting the entire amount of information from so that the transition between the electrical signal and optical signal, that is not good. So that's why we have to calculate the bandwidth, how much bandwidth the electrical signal can give the optical signal, at which so different frequency or pulse signal you can provide. So it's not only possible all the pulse kind of the signal can provide the same kind of the optical signal. Normally if want to give the high frequency signal, it's very difficult to. So the high frequency signal means the electrical signal is on off very fast. This is the high frequency signal on off very fast. Okay, so it can very difficult to generate the respective optical output from the electrical output. If the response is very low, then you can get the easily exact output as which if you compare the electrical signal. So this is the modulation bandwidth. Normally, how can you define the mono? The output optical power is reduced by the 3 dB with respect to input power. So, if you are giving some input power, if that is, if you are getting the optical, so whatever input power you are giving or not getting, if the pulse is not same, that means you are not getting the same output power, input power at the output side. That means the optical power will, there will be reduction of the output power as compared to the input power. How much reduction? There will be the 3 dB is the margin point. So if output power is reduced by 3 dB with respect to input power, that much bandwidth is that much duration is called the modulation bandwidth. And the 3 dB point, how can you define the 3 dB point? Ratio of the current is half. If the ratio of the current is half, that depends. So I'll show you the next diagram. So electrical, there is two bandwidth. One is the optical the modulation bandwidth or optical bandwidth, and another is electrical bandwidth. Electrical bandwidth means the electrical signal power dropped to half of the maximum power input power. That is the electrical bandwidth. Okay, the electrical signal power dropped to half of its constant value, resulting from the modulation portion of the optical signal. So whatever the output optical signal you are getting, so from that you can get some electrical signal. So in this way you can get the electrical bandwidth. So electrical bandwidth is not too much important for this case. Optical bandwidth is important. So electrical 3 dB point, how can you define? The frequency at which the output electrical power is reduced to 3 dB with respect to input optical power. This is the electrical 3 dB point. Okay, so in case of the electrical 3 dB point, how can you are directly when the optical electrical power is reduced to 3 dB, that is the electrical 3 dB point. But in case of the modulation bandwidth or optical 3 dB point, so that means in this case you are calculating the ratio of the current, which is half. Okay, that is the 3 dB point. Because in case of the optical power directly proportional to the current. In case of the electrical power, the optical power is now not directly proportional to the current. So the electrical power is the I square R. Okay, but in case of the optical power, normally the I is equal to I proportional to P. This is the relationship between the current and the power, optical power. Okay, and this is the relationship between power, electrical power and the electrical current. Okay, so I proportional to P here, I proportional to P or P proportional to I here, P proportional to I square R. So in this way, so both are the, here the current ratio is not same as the current. Here current ratio is half. So for this case current ratio will be 1 by root 2. Okay, this I will tell the next slide. Next slide. Okay. So now here you can see you have plotted the graph. Here the optical, so that is the maximum optical power. Suppose maximum optical power, you should get this in input power. So this power you are giving to the input side of the LED. So the power will continuously decrease. As the speed is not fast, due to the response time, the power will be decreased. Okay. So in case of the optical power, what I told, that it will be bandwidth can be defined when the optical power reduced to the by 3 dB of the initial power. That is the here the 3 dB. Okay. At that moment, at this moment, where the power is reduced by 3 dB with respect to input power, at this moment the ratio of the current is half. Okay. Here I have the graph is between the ratio of the current and the frequency. At this moment, the ratio I out by I ratio of the current is half. So this is your optical bandwidth. But in case of, so here you can see the optical ratio is the tan log P output by P input. Okay, so here in case of the optical case, the P directly in place of P you can directly write the I. Okay, in place of P you can directly write the I. So tan log I omega by. But in case of the electrical ratio is also the ratio of the power we are defining, tan log P omega output by P input. But here P is I square R. Okay, here also P is I square R. So tan log I square omega by I naught square. So that means the define is that the this will be half. Okay, this is the half. This is half. Okay, that means this and this both are same. Okay, the ratio is the half. What the definition is that how can you define the electrical, optical bandwidth where the power is reduced to 3 dB of the initial power. At that the same moment the ratio of the current is also half. Ratio of the current is half. So this is the ratio of the power and the ratio of the current. So both is equal to half. Okay, so the this power and this power you can consider the same power, this power and this power. So this is half means, so this ratio is also half. Okay, this ratio is half. So that way you can define this thing. Okay, the ratio is half means the then I square omega by I naught square omega, that is half. Okay, half means the I omega by I naught is the 1 by root 2. Okay, 1 by root 2. So in case of the electrical concept, the I omega by I omega 0, I output by I input is the half. In case of the electrical concept, the I output by I input is 1 by root 2. So that's why if you want to, from the same I process frequency graph, you want to measure the optical bandwidth and electrical bandwidth, both are the different. So in case of the electrical bandwidth, suppose the current is reduced half. So this is suppose the optical bandwidth. So here the half, here is 1 by root 2. 1 by root 2 is 0.7. Okay. So this will be the electrical. So this will be the electrical bandwidth and this will be the optical bandwidth. If you want to calculate the ratio of the current versus frequency graph, you want to calculate the both bandwidth from the ratio of the current versus frequency graph. Now, here I will start to discuss some numerical related to those things whatever I discussed today's class and the previous class. So there is a numerical. The LED has the 5 nanosecond injective carrier lifetime. So the tau carrier lifetime you can remember the tau. Tau is the 5 nanosecond. Okay. So tau is 5 nanosecond. Okay. So where no modulation, the current is applied to the device. The optical output power is the 0.25. So that means no modulation. Whatever input power you are giving or getting the same optical power. So that is the P naught. Okay, so P naught is the 2.25 milliwatt. Okay, and for the specific DC bias, that's why I told the no DC input signal you are giving, so you are getting this signal 0.250 milliwatt. Assume that the parasitic capacities are negligible. What are the optical output at the modulation frequency? The 10 megahertz for 100 megahertz. The formula is like that. If you recall the formula, then P omega is equal to P naught by root under 1 plus omega tau whole square. Okay, that is the formula. So P naught is given 0.250 milliwatt. Omega means is equal to 2 pi f. Omega is equal to 2 pi f. So here you can for two different omega, you have to calculate the p omega. Okay, one is for 10 megahertz, one is for 100 megahertz. So from here, if you put the value of frequency, you can get the omega. Omega, you know, tau also, you know, 5 nanoseconds, and you can calculate the value for p omega. This is for 10 megahertz, this is for 100 megahertz. So two different optical power you will get. So this is the simple thing. If you know the formula, you can calculate, solve this numerical. Next is this one. Consider the particular LED described in the example, which has the 5 nanosecond carrier lifetime. The same, comparing the same 5 nanosecond lifetime. What is the 3 dB optical bandwidth for this device? What is the electrical 3 dB bandwidth for the same device? Okay. For case of the electrical optical bandwidth, optical bandwidth is the half of the input optical bandwidth. Okay, P omega is equal to half of P naught. That we know, right? So that means instead of P omega, I can write this formula P naught by root under 1 plus omega tau. Okay, this formula I have mentioned. Right. So if you substitute this one, you will get the omega tau is equal to root 3. And what will be the f? F is equal to, instead of omega, you can write the 2 pi f, then f is equal to root 3 by 2 pi tau. The tau is the 5 nanosecond. So this is the f. So this is the bandwidth for the optical. Okay. And the electrical bandwidth will be the optical bandwidth by 1 by root 2. The ratio also told, na? The ratio is the 1 by root 2. Okay, so that's why directly you can write the electrical bandwidth will be optical bandwidth by 1 by root 2. Okay, so this is your electrical bandwidth. Next, related to the band gap and the material. How can I? So, if you recall the previous equation, or you can see my previous lecture, so there is a relationship between the band gap and the molar ratio x. Okay, so 1 point Eg is equal to 1.424 plus 1.26 x plus 0.66 x square. Okay, so here the value of the molar ratio, the constant material ratio x is equal to 0.7. Then find the band gap of the material. So just we'll put the value of x in this equation and we will get the band gap of the material. Okay, you can get the band gap of the material. This is 1.51. And the peak emission wavelength. So Eg is equal to, you know, that 1.24 by lambda, where lambda is in micrometer. Okay, so if you put the 1.51 here instead of Eg, if you put the 1.51, you will get the lambda is in micrometer, the 820 nanometer. The same way you can also solve this equation. Okay, you can also solve this equation, that is for x, this different equation. Here you have x is also given, y is also given. So there is a relationship between y and x, and again there is one relationship between x and the y and the Eg. So from these two equations you can get the value of the Eg, and again Eg is equal to 1.24 by lambda. By using this equation you can get the emission wavelength. So this I am not elaborately describing here. So this is the numerical. So there is a double heterojunction indium gallium arsenide phosphide. The LED emitting wavelength is a 1300 nanometer. The LED can emit this wavelength light. Has the radiative non-radiative recombination of the 30 and the 100 nanoseconds. So radiative recombination and non-radiative lifetime. This is 30 nanosecond, 100 nanosecond. So if you want to calculate the bulk recombination rate, so tau r into tau r, and this equation I discussed in the last class, the tau r by tau n divided by tau r plus tau n. So if you put the, you can get the bulk recombination lifetime. So what is the internal quantum efficiency? The internal quantum efficiency, if you recall the formula, that is equal to total bulk lifetime divided by radiative recombination lifetime. So if you divide both you can get the 0.7. Second is the third is the internal optical power. Internal optical power, again if you recall the formula, the P internal is equal to N in efficiency into HC I by Q lambda. Okay, it's I by q lambda. The driver current is the 40 milliampere that is given. Driver current 40. So instead of I have to put the 40 milliampere. HC value, you know, it is that this one 6.625 into 10 minus 34 J. C is the 3 into 10 to the power 8 millimeter. And eta, you know, that is 0.77. Q is the 1.6 into 10 to the minus 19. Lambda is the, here you can see the lambda is 10 nanometer. Okay, so here I have given the value for C is in meter. Okay, so then you have to convert the nanometer to meter. Okay, so if you calculate this one, you will get the 29.9, 29.2 milliwatt. So if you recall the each and every formula, you can easily find out the, you can easily solve this numerical. So please like, share and subscribe my channel. Thank you. And last class I will start with the laser.